right, so what we're going to talk about today is how Boyle's Law came to be. Now, I can't find my thing. Oh, here it is. Sorry, I was looking for it. All right, so this data, it's from your book. This is actually table 5.1 on page 168. Now, you might remember Boyle's Law as as P1 V1 is equal to P2 V2. All right, now I'm going to explain how this came how this came to be. All right, so last time we talked about these J tubes, right? And I didn't go into too much detail of them, but I'll explain how Robert Boyle used them to come up with Boyle's Law. So I explained how gases how they were able to isolate gases at the time period. So they filled up a container, right? Gases fill up the entire container. So he filled up this container and then added mercury in here, and the mercury pushed the gas all to one little corner. All right, so what did he do? Well, the gas pushes the mercury and the mercury goes up, so that's how he measured the pressure of the gas. All right, he measured the pressure from the gas, and then he just took a little ruler, measured the millimeters or the and calculated the volume of the gases there. So he knows how much volume, and then he knows how much pressure, how much force it applied back into the mercury. And oh, sorry for shaking the screen. Sorry. Now he did this multiple times at multiple days. So he got another amount of gas, put it in the J tube, and measured how that one affected the pressure, and kept on going lower and lower and lower. So he was trying to establish a trend or a pattern and trying to recognize which pattern he would see. So this is actual data that Boyle collected, and I'm going to show you how he came up with this gas law. All right, well, while trying to explain to derive a how would you say an explanation to what he was observing, multiplying the two values of pressure times volume. All right, now if you do that, if you get 117.5 times 12, so go ahead and put that in your calculator. 117.5 times 12 is 1,410. All right, and you do the same thing with the next one, 87.2 times 16, and boom, you get 1395.2, and you keep doing this, and then you'll find a pattern. Now I'm going to show you a faster way of doing this. Right, you highlight it, Control C. Go to a Google Sheets, and we'll open up a new one. Go to Google Sheets, paste it, right? Paste it. Highlight the cell that you want to write your things in. So we're highlighting the C2 cell right now. Click on it, put equals, and now we're going to do the pressure times. So we're going to put the asterisk. The asterisk in this case, it means multiply. So we're going to multiply times the volume, and we're going to hit enter. And it gave us that same value we had. Now, we want to apply the same thing to the whole sheet. So you grab it from the corner and drag all the way down, and it does that calculation for you. All right. Now, I also asked for the inverse of pressure here. I asked for the inverse of pressure. So how do we do that? We put equals and 1 divided by, and whatever our pressure is right here. So we hit enter. And then autofill. Okay? Excuse me. Now, but ignore the 1 over pressure. I really want to focus on, whoops, where's the redo? I always forget what the redo shortcut, Control Y. All right, the main focus I want is this little area right here. When pressure times volume, when you multiply the pressure times the volume, you get a number that's basically the same regardless of the pressure or the volume. Very few differences every once in a while, like right here, but for the most part it is the same till like the last digit, or the last two digits. But not bad for not having digital instruments. This is all using rulers, so very, very impressive. So what does it tell us? It tells us that pressure times volume is equal to some number. We'll call that K, a constant. So the first pressure and the first volume that we recorded multiplied together gives us that K. We do the same thing with the other one. We'll multiply these two. Well, that's pressure 2 times volume 2 is also equal to the same number. Well, now since the variables are the same, you get the formula P1 times V1 is equal to P2 times V2. And that's the relationship, and that allows us to determine the pressure and the volume if we know the initial pressure and the initial volume. All right, so it's going to be the same ratio. It's always going to be the same ratio. Now, this idea that Robert Boyle proposed, right, the relationship between pressure and volume, inspired other scientists, right? Avogadro came up with the idea that if this relationship exists, and this relationship exists for different types of gases, right? Boyle had tested this with a bunch of different gases, and Avogadro was like, well, if these are all different gases, then the atom type doesn't matter. All gases must behave in that same similar fashion, and that is eventually what led to the idea of the mole. All right, that the gases have the same number of particles, and he came up with the conclusion that 22.4 liters was equal to 1 mole. All right, so Avogadro, smarty pants, he used other people's experiments. Boyle's the one that did all the work, and Avogadro just came up with stuff afterwards. So that guy, he knows what's up. So hopefully this equation gives you a general understanding of how the other equations were kind of derived. I'm not going to do this for all of them. I just wanted to explain Boyle's because I think it's the easiest one to explain. And if you don't remember from, well, hopefully you remember from the last video, where all of these properties are kind of just related, right? We look at these, the pressure, the volume, the temperature, and then the number of particles. They all kind of have their own effect, and they affect each other. So although there is multiple gas laws, they can all be combined into one. And we'll talk about that a little bit later. I think this is enough for this section. Now what you're going to do is you're going to plot in one of these, right? You're going to plot the pressure and volume, right? So it's going to be, I'll explain right here. I have them off to the side. So your pressure is going to be on the y-axis, and your volume is going to be right here. And in the bottom one, it's going to be your volume here, and then 1 over pressure on your x-axis. And what I want you to really see is this graph, how it becomes a straight line. And what does that relationship tell us? Well, that relationship tells us that if pressure goes up, that when pressure goes up, that means volume has gone down. Or if pressure has gone down, that means volume has gone up. Why am I writing slanties? Stop it. So as pressure goes down, the volume goes up. And I demonstrated that with this right here. You lower the volume, you increase the pressure. You increase the volume, you decrease the pressure. So that's Boyles Law right there. All right. Now, graph those and the conditions. The conditions in Boyles Law. Boyles Law assumes that the temperature and the number of particles are the same. All right. So you must keep those two constants, and that's the only time that you can actually use Boyles Law. Now, also, it has to be what we call an ideal gas, and we'll talk about those later. All right. Oh, K is the gas constant. I think I said that. K is the gas constant.